Okay, thank you very much. I'd like to start by acknowledging my co-authors, my PhD student Susan Zhalehpour. We had an intern from BUPT, Beijing University, who was with us, and the other members of the team. I'm at the Université Laval in Quebec City, Canada, and within the Center for Optics, Photonics, and Lasers. So the motivation for this talk is about using Mach-Zehnder modulators. I'm going to talk about modulators, but the reason the modulator is important and that I'm interested in doing all silicon is because, of course, silicon is very good system for creating an entire subsystem of components, not just the modulator. And of course, because it's produced in a silicon foundry, it's also compatible with all the electronics that goes with it. So we concentrate on the modulator in this talk because of where we want to put it in the entire subsystem to get the advantages of low cost, low power, and small footprint coming from the all silicon solution. So if we look at modulator performance over other processes such as lithium niobate, indium phosphate, and silicon organic hybrid, we can see that the performance has been well established at 100 gigabaud operation at both single and double polarization at various times. And if we go into an all-silicon solution, we've seen the gradual increase in performance of these modulators up to the 100 gigabaud at OFC last year, and these results take the 100 gigabaud, but now we apply it both to dual polarization as well as single polarization, which brings us to the title, which says we can reach a 1 terabit per second line rate because of the exploitation of dual polarization. Of course, the objective here is to show that it is possible with all silicon to reach similar performance achievements as we've had in other materials. So although the focus of my talk is not on the modulator in itself, this was designed a year or two ago, I'd just like to refer you to the literature if you're interested in knowing more about the design of the component itself. It is a traveling wave modulator. We use a single drive push-pull configuration, and there was a slow wave electrode designed into it. I show you on the right a photo of the experimental setup, physical setup, so that you have an idea of what was involved in the experimental results I'll be showing you. So the challenge is to push the bandwidth in exploiting this modulator, and that involves a lot of system optimization, and including how, first of all, just to operate this modulator. So to give you an appreciation of why this is important, I'd like to just show you the small signal response for the modulator for various bias levels. So depending on which bias you set your modulator at, you will get different bandwidths. If you want to define the bandwidth as a 3 dB bandwidth. And of course you would think, well, this doesn't look too difficult. If I want to have a wider bandwidth for my modulator, I'll simply operate it at the appropriate bias point. The problem is that when you adjust the bias, you adjust not just the bandwidth, but also the Vπ of the modulator, which is different from other materials. So, for instance, you might increase the bandwidth by your choice of V-bias, but the Vπ depends on V-bias, and you might actually decrease your modulation efficiency. So there's just, even when you start off, the first time you manipulate your modulator, you have to find a good bias. So the first thing we do is, depending on the baud rate and the modulation format we're looking for, is we find a good trade-off, looking at the bit error rate on what would be a good bias. So that's our first point. Then the next, I guess I should just point out, this is the small signal model. And of course, when I'm operating my modulator, I'm making much larger swings than what is involved in this characterization measurement. And because of that, you can tell that the modulator is intrinsically has a nonlinear response because the frequency response will vary depending on how I'm driving. As I swing through the 2 volts For instance, I'm going to go through the equivalence of different bias points, and that's going to change the frequency response. So because of this, I'm going to have to attack this both in terms of linear and nonlinear compensation. So the first thing we do is we attack the linear. And so I look at my modulator and I say I'm going to add an optical linear equalizer. And I look at the depth of the response I can put into my optical filter, and I vary that. I sweep the depth, and I find something that looks pretty good. Then I go and I put in a digital pre-equalizer. So I'm doing splitting it between the optical and the digital domains, and I jointly optimize that so I can get the best linear response I can from this modulator. So I've done the linear pre-compensation so far, and now I start looking at what I can do at the receiver side. What can I do for my post-compensation? And I use nonlinear post-compensation because I realize that it's necessary for the system. There's two stages. The first stage is a nonlinear filter. So I'm basically doing a polynomial least squares, first and third order terms, so a Volterra type nonlinear filter. And again, that takes care of this, is trying to address this challenge we have in the modulator itself having this nonlinear response. Now, there's also a second stage I introduced to the nonlinear processing, and this has in some way to undo what harm I might have done myself in the linear compensation, because of course when I do my linear pre-compensation, I'm pre-emphasizing a little bit the noise, so I'm enhancing the noise in some frequency domains. And so what I do at the second stage is basically I try to whiten the noise, we can think of it this way, that I'm introducing a low-pass filter parameterized by alpha. And so in a way, I'm creating intersymbol interference at the receiver. However, this is a very controlled structure ISI, and because of that, I can use a maximum likelihood sequence detector, which is exactly matched to the low-pass filter that I introduced, parameterized by alpha. And so that's very low complexity. It's not a long, it's actually a one-tap maximum likelihood sequence detector. So all of this in order to do the best that I can in the nonlinear regime at reasonable complexity. However, I'll show you some bit error rate curves. This is not sufficient to achieve something like the 1 terabit per second results that I'm going to do. And so what we need is an additional step of nonlinear pre-compensation. And in fact, this is key, that if I just use the post-compensation alone, I will never be able to get within underneath effect threshold. But I can do this by using pre-equalization. So the way that we do the pre-equalization is we train it with hardware in the loop adaptation. We use frame averaging so I can get rid of some of the noise, and it's fairly quick convergence, takes about 8 iterations, takes about 15 minutes in the lab when we're running this in quasi-real time. There's details in our previous papers, but basically we're using iterative learning control with a nonlinear adaptation, which has the acronym of the GILC is the method. So here is the sort of block diagram of what goes on. We start with a standard 32-QAM constellation, and then we pre-equalize it using our trained ILC equalizer. Then we put it through the linear pre-compensation. We go through, of course, there's the DAC. There's many points where nonlinearities are introduced in this system. First is the DAC, also in the RF amplifier, which is not even shown here, and of course the silicon modulator itself. So we go through the modulator, through the optical filter. Of course, there's also linear compensation, post-compensation, and the nonlinear. This is the setup used in our experimentation with the DSP and the blue blocks on the side. So these are the results that we presented last year at OFC for single polarization. I'm just showing it for 16 QAM. We had similar results for 32. It's a little easier to see for the 16 QAM. And you can see for 16 QAM without the pre-compensation, applying all of the linear compensation, all of the nonlinear post-compensation, the best that we could do, we would get the curve and dashed. And when we introduced the pre-compensation, we had our biggest improvement. And this was enough for 16 QAM to go over the 7% threshold, and for 32 QAM, it got us under the 20% effect threshold. So when we were doing the training part, this green part, when we were training our nonlinear pre-compensation, we had a method where we would take our typical receiver chain, and we would do the frequency offset and the carrier recovery in a blind fashion. Then we would use our training sequence for our linear compensation, and we would do a lot of frame averaging, as I mentioned, to bring down the noise. We're working with a bare chip, and so we have a lot of noise because we need a lot of amplification to overcome coupling losses. And because you see this is called method A, you can imagine that it didn't work very well when we moved to dual polarization, and that's why there's going to be a method B. So when we tried the same approach to training our nonlinear precompensator, we really didn't get very far. This is the results for single polarization, where you can see that the number of iterations is at the bottom, and that we could, get a fairly good reduction in the error in our precompensation routine, both at 16 and 32 QAM. But when we tried it for dual polarization, putting in a polarization emulator there, first of all, we took a 3 dB hit on the noise. Second of all, these nonlinear interactions, of course, will work differently in 2 dimensions than they did in 1 dimension. So therefore, we went to a second method, and in our second method, we had to introduce, when we tried, first of all, it was just training our nonlinear precompensation on 1 polarization, but that was not sufficient, so we had to go into the MIMO processing in a data-aided situation. It didn't really matter for the frequency offset compensation or carrier recovery. It was doing well whether it was data-aided or blind. And again, the MMSE could be data-directed, data-aided in the method B. The important thing was to do the compensation here at the IQ stage, and of course lots of averaging. And in the end, this was just a much better way to do our convergence. I probably should have done it first on the single polarization, but we were getting decent results without it. But coming up with a better way to allow our quasi-real-time adaptation to have a better view of what the nonlinearity remaining to be compensated was, by doing a better estimate beyond the noise, allowed us to come up with a much lower error in our precompensation. So these are the final results we see. We have a bit error, going back too far. We start with bit error rate, and first we look at X polarization, Y polarization, and then an average over the 2 polarizations. We start here with, in black is the 32 QAM, and in blue is the 16 QAM. And as with the single polarization for 16 QAM, the 7% overhead FEC, we could meet the FEC for 7% overhead. However, at 32 QAM, we had to go to a 20% overhead FEC level. This was only using a linear post-compensation at the receiver side, and if we combined our nonlinear pre-equalization with nonlinear post-equalization, of course we could improve significantly the margin at 16 QAM and also gain some more margin at 32 QAM. So in conclusion, I'd just like to say that we've established that an all-silicon solution can rival data rates of more established integration platforms. We're able to come close to performance demonstrated from those platforms. In particular, we achieved 32 QAM, 100 gigabaud. The line rate was 1 terabits, and if we take into account the 20% overhead for FEC, we get a net rate of about 833 gigabits per second from the all-silicon modulator. But the important lessons we learned is the optimization that has to be done at very many levels, starting from just the operating parameters themselves to the DSP used at either receive or transmitter side. So thank you for your attention.